Hi everyone, this is 7.5 Notes and the title is Parts of Similar Triangles. Kind of a simple concept. If two triangles are similar, then their parts are similar. So we're going to talk about what those parts are, introduce some new vocab words, and the second main topic of this set of notes is introducing and using the triangle bisector theorem, which is kind of an odd duck. You'll see when we get to it that it shows proportionality between two pairs of sides, but those triangles are not similar, so it's very non-intuitive, let's say, this theorem. So we're going to go into detailed proof of it. So let's talk about the parts first. It kind of makes sense that if two triangles are similar, their parts are similar. First part is a mid-segment. A mid-segment we've already gone over, but let's just review it. If I call this ABC, a mid-segment, and there are, remember, 3 mid-segments in every triangle. A mid-segment has this, let's call this DE. It's parallel here. So DE is parallel to CB. And what else can we say about that mid-segment? D is a midpoint of AC. And E is a midpoint of, I'm sorry, I forgot AC over here, AC of AB. And we know that the mid-segment theorem says that the length of DE equals 1/2 the length of CB. So that's one of the mid-segments. Of course, we can draw 2 more mid-segments, as shown in the last section of notes. A median. A median connects, it's basically a segment from one vertex to the opposite side, and where it's connecting to the opposite side is at that opposite side's midpoint. So hopefully you can sort of anticipate that there will also be a quantity of 3 medians in every triangle. So if this is A, again B, C, then let's draw a vertex. If I try to find, for instance, the midpoint here of CB, then that right there, I'm going to call this D. AD is a median. And again, I hope you can anticipate that there will be 3. I can draw from vertex B across over here to this midpoint of AC. Likewise, draw a segment from C over here to the midpoint of AB. So there'll always be 3 here. Altitude, height. This one you should know very well already. So if I, again, just say A, B, C, the height of a triangle is the perpendicular drop. Comes straight on down. I'm going to erase that because it's messy. So it comes straight from one vertex perpendicularly to the opposite side. So this is the altitude. I'm going to label this point D again. So here AD is the height or the altitude. Those 2 words are one and the same. So if we were to describe it, again, it's a segment from one vertex, sorry my writing is so messy, to opposite side. And instead of to the midpoint, it will be perpendicularly. Creating this 90-degree angle here. And hopefully you can also see that I could do the same thing from B. I can draw a line right here from B to the opposite side perpendicularly, And likewise, from C, it's going to go almost like that perpendicularly. All right, remember though, for the altitude or height, if you have an obtuse triangle, that height or altitude is outside of the triangle, so do remember that. Angle bisector. Angle bisector, of course, bisects an angle, cuts an angle into two equal halves. So if we take this same triangle we've been using all along, and I've got this angle here, I want to look at how can I cut that angle into, oh boy, that's messy. How can I cut this angle here, into two equal halves? So I've got this angle, I'm going to try to go, I'm sketching, and that I've done a terrible job of it, but I'm sitting here writing with a very fat stylus. So here I'm trying to show that this angle is being cut into two equal halves. And again, hopefully you see that we can do that for all three vertices and therefore have three angle bisectors. So we go from, we're going to go from each vertex to opposite side such that we are bisecting the angle there. That means two equal halves. So my sketch is not great, but when we bisect that angle, it comes down, it's not hitting this midpoint like we are seeing up here for the median. This angle here, cutting it into, this is a smaller segment than here. So please note that. I'm going to go ahead and call this again D. So here in my example, AD is an angle bisector. And it's specifically bisecting angle CAB. All right, great. So what is the theorems that we're going to look at? Well, when two triangles are similar, all their parts are proportional at the same proportionality as the sides. So pretty simple concept. Here we've got special segments of triangles. The first one is altitudes or the heights. If these two triangles are similar, i.e. they are proportional, then their heights or altitudes are at the same proportionality, same ratio. Kind of makes sense. The next one, if we have an angle bisector, these two triangles happen to be similar, and we have angle bisectors of each of those triangles, well, the length of those angle bisectors are proportional at the same ratio as the sides. Makes sense. Now, I'm going over this very fast, but as I mentioned to you in class, any of these notes that I'm giving you for diagrams and theorems, you should be spending some time digesting them after class. You should be reading this and understanding them. You should, for example, be going through these exact ratios here and trying to make sense of them on your own. And finally, if two triangles are similar, then their medians are also proportional at the same ratio as the sides. So here we're showing medians, and we know they're medians because the sides opposite are being cut into two equal halves. I can't stress enough how important it is, I should say, that you look through these theorems, read them, make sense of them, look at each proportion that's being written here. And the one that's not being shown here is the mid-segments, and I'd like you to think about the mid-segments as well. They're also going to be proportional to the same ratio as the sides between two similar triangles. So please take some time and read this beyond what you're listening to right now. The last thing in this section that's kind of peculiar, as I mentioned, is called the triangle angle bisector theorem. This I will spend a lot of time on here. So what does it say? It says that If we have an angle bisector in a triangle, so I know this JM is a bisector because these two pieces of the angle are being marked as congruent. It says that if you do have that angle bisector, then these pieces here that are created on the opposite side, KM to LM, is at the same ratio or proportionality as these outer sides, KJ to LJ. And that is kind of strange because those two triangles are not similar. How do I know that they're not similar? One side of each triangle is in both triangles. So JM here is reflexive. The length of JM is equal to itself. Okay, we do have two congruent angles in both triangles, but this side here is congruent to itself. So how can these sides be proportional with these outsides? It doesn't make any sense that two out of the three pairs are proportional where one of the pairs is equal to itself. It just, you cannot obtain side, side, side here from this circumstance. So on the surface, you look at this diagram and there's no way that these two triangles are similar. How can these pieces here be proportional? And it is true that they are proportional, but it's in a very strange way. So I've put together a proof for you. It's kind of complicated, but I do think it's important that you know why this proportionality arises. So let's take it one step at a time. All right, so we have a triangle. I'm going to try to highlight it here. We just have a triangle, and it's A, B, C. My highlighting is kind of messy. We have a triangle, and we have an angle bisector. I know that BD is an angle bisector because these two resulting angles are marked as congruent. So we're trying to prove that BD, if it's bisecting that angle, then I'm trying to prove that AD to CD, AD to CD is proportional to these outer sides, AB and BC. And in order to do that, we need to draw some auxiliary lines. So that's what these things are all about here, these dotted lines. They're not part of the original diagram. All right, so we have a triangle, we have a bisector. I'm going to draw an auxiliary line CE such that it is parallel to AB. So here I've got my parallel lines marking. I'm going to draw this line here down. It's not part of the original drawing, but I'm going to draw it straight down such that it's parallel to AB. And that's just the definition of an auxiliary line. I could draw any auxiliary line I want to help with my proof as long as I define it. Next, I'm going to draw another auxiliary line DE, and I'm just going to extend that angle bisector all the way down until it intersects with this CE parallel line that we have already drawn. So again, that's a definition of an auxiliary line. So it's just helping aid my proof here in some way. Now, angle ABD, so angle, let's see, ABD, this angle, is congruent to DEC, DEC. So angle ABD is drawn with a single arc, and we're saying that it's congruent to DEC. Why is that? Well, that's on the inside of a Z pattern of parallel lines. So those two angles are on the inside of a Z pattern. We know that that means alternate interior angles. Alternate interior angles. And we have BC is equal to CE, or congruent. BC is equal to CE. Well, this angle here is also congruent to this angle. So hopefully you see that this is an isosceles triangle that we just developed here. We've got base angles that are congruent, therefore the sides opposite are congruent. So that would be the converse of base angles. So let's mark what we've just discovered here. These two sides are congruent. Next, the angle BAD. BAD is congruent to DCE. So I'm going to mark that here. I'm going to mark it red. This angle is congruent to DCE. And hopefully you can see again that's on the inside of a Z pattern of parallel lines. So again, that's alternate interior angles. And we have angle BDA. BDA is congruent to CDE. And I'm going to mark that also in red. I'm going to use 3. Now, we can say vertical angles or third angles theorem. It doesn't matter which. Let's write them both down if I could squeeze it in. Vertical angles or third angles theorem. Yeah, I'm going to abbreviate that. I have no room. And then finally, why are the two triangles similar? I almost said congruent. Why are the two triangles similar? Well, angle, angle, angle. All three pairs of angles are congruent. So if they are similar, then AD, let's look at that. AD is between the double and the triple arc. AD is to CD, also between the double and the triple, as AB, between the single and the double, is to CE. Well, we can say corresponding sides of similar triangles are proportional. I'm going to have to abbreviate there. And finally, how do we prove that these pieces here are of that same proportionality? So AD is to CD, as AB is to BC. Well, what are we doing there? All we're doing, everything is the same between the row above it and the row below it, except CE is now replaced with BC. And hopefully you can see why we did that. They are congruent because they're part of that isosceles triangle. So all we're doing there is substitution. So this is somewhat of an odd phenomenon that happens when we have this angle bisector. When we have this angle bisector arise inside this triangle, it creates some proportionalities of sides that are not because the triangles are similar, because they are not similar. But it is an interesting result nonetheless. All right, let's try to work a couple of problems here. In the figure, we have two similar triangles, LJK and SQR. Find the value of x. Well, hopefully you're going to get comfortable with some of the parts of triangles here. And these segments here are going from one vertex to a midpoint on the opposite side. So MK and TR are medians. So you are going to need to know this vocab here. They are medians. Those medians between two proportional triangles are going to be at the same proportion as the sides. So we've got some things here marked. We've got x here, x length, and it's congruent here, so that's also x. And we've got 5 here. It's being marked congruent because it is connecting midpoints here, so that's 5. All right, great. So we can look at some sides. We've got proportion we can write. Let's start with the medians. So MK is to TR as, we can say the sides here, JL is to QS. MK12 is to TR8 as 2x is to 10, 5 plus 5. Oh, that doesn't look like a 10. Sorry, it looks like a B. So we end up with 12 times 10 equals 16x. Divide both sides by 16. And we have x equals, let's see if we can simplify here. 12 divided by 4 is 3. 16 divided by 4 is 4. 10 divided by 2 is 5. And 4 divided by 2 is 2. So I've got 15 divided by 2, x equals 7.5. Next, we have some altitudes or heights. So BD and GJ are altitudes. And we are told that these two triangles are similar. Therefore, we know that the altitudes are going to be at the same ratio or proportionality as the sides. So I can say, let's say BA, the side, is to GF, as BD is to GJ. So we've got 21 over x is to 9 over 6. I've got 9x equals 21 times 6. And I've got x equals 21 times 6 divided by 9. Let's see if we could simplify. We can divide 21 by 3 and get 7. And 9 divided by 3 and get 3. And then 6 divided by 3 is 2. So we end up with x equals 14. Number 3, this is where we've got that odd theorem, the triangle angle bisector theorem. And we've got this angle bisector cutting this angle into 2 equal halves. And the vertices are not labeled, so I'm going to label them just to help some people see what's happening here. So the theorem says that if you have this angle bisector coming down, then these pieces that are created over here on the opposite side are at the same proportion as these outer sides. So I'm going to say BD is to, I'm going to use its outer side here, AB, as CD is to its outer side, CA. So I've got 6 is to 9, as x is to 15. Cross multiply, I have 9x equals 6 times 15. Divide both sides by 9. Try to simplify. 15 divided by 3 is 5. 9 divided by 3 is 3. And 6 divided by 3 is 2. And we have x equals 2 times 5, or 10. And finally, same thing. We have a triangle angle bisector. I don't like the way this almost looks like an arc going across there. They're slightly offset. I'm going to try to offset them a little bit more than the textbook does. But let's again label A, B, C, D. I think it's easier. And so we know that these pieces here are proportional to these outside pieces. I'll try to do something a little bit different this time. The last problem I said BD to its outer side, AB. You don't have to always do it that way. You can say CD is to DB. CD is to DB. And then since CD is over on the left here, use AC on the top. And DB is on the right, use AB. Doesn't matter how you set this up as long as you're consistent, because if you are, then when you cross multiply, it'll be exactly the same equation that you're trying to solve. AC is N, AB is 21. We've got 21 times 5 equal to 7N, and we've got N equals 21 times 5 divided by 7. Notice I don't even do the multiplication because it's so much easier if you just simplify before doing it. So N equals 15. Thanks for listening. Hope this helps.